Welcome, everyone. I see we still have some people coming in, but let's go ahead and get started with some introductions, and more people can join us as we go through that. Welcome to the Data for Impact webinar on managing missingness and routine health data. I'm Jessica Farringer, Technical Director of Data for Impact. And for those unfamiliar with Data for Impact, or DFRI, we are an associate award of Measure Evaluation, and we continue Measure's legacy of building evidence to improve health systems and programs. DFRI supports countries to generate and use high quality data to improve their programs, policies, and ultimately, of course, health outcomes. We also strengthen the technical and organizational capacity of local partners to collect, analyze, and use data. This is our second webinar in a series that's sharing lessons learned and practical suggestions on using routine and other existing data for evaluation and research. The first webinar you can find on our website, the Data for Impact Project.org website. That was on using routine data in economic evaluation. And the third will be in February. You can be on the lookout for an email announcement or on our website about that webinar. We're still working out the details. We created this webinar series with the goal of providing practical information that helps global health evaluators and researchers to make better use of routine and other secondary data. Evaluators and researchers often have avoided use of such data, preferring to use other data sources like standalone special surveys designed to meet specific evaluation or research objectives. However, in light of the potential cost and time savings compared to collecting primary data, we think it's important to consider routine and other existing data. They, of course, come with their own set of challenges to consider and address. And today's session will shed light on one way to address the challenge of missing data. We'll be exploring this through use of District Health Information System 2, or DHIS2, data from the Democratic Republic of the Congo, or DRC. So then with that background, let me introduce you to our presenter. Matt Worges is a monitoring and evaluation specialist with Data for Impact and a PhD candidate in the School of Public Health and Tropical Medicine at Tulane University. His current research includes assessing the impact of a DRC-based health system strengthening project designed to increase access to and use of health services. So with that, Matt, I turn it over to you.
Thanks, Jessica. That was a great introduction. I think it frames really well what we're going to talk about today. Thanks everybody else for joining us this morning too. So this talk is called Managing Missing Values and Routinely Reported Data, one approach from the DRC. And this is truly just one approach to handling missing data. For those of you who have worked through this process before, I'm sure you're aware of the numerous methods that exist to try to handle missingness. So the approach that I'm going to discuss is by no means the definitive approach, but I hope that there are some useful nuggets in here, some good takeaway messages. During the Q&A portion of the webinar, it'd be great to hear if anyone else has had alternative experiences or if they could share some of the approaches that they've used. But let's go. So to loosely frame the webinar, I'll make initial reference to the ongoing impact evaluation work that I'm doing alongside the D4I team. We'll take a look at data that I pulled down from the DHIS2 from the DRC and explore it while assessing certain advantages and issues to using these data. A major obstacle to working with DHIS2 data in the DRC is the issue of trying to distinguish missing values from zeros. Especially considering that zeros are not always entered into the system. I'll explore three basic interpolation methods, and apologies to anybody who was expecting this, but I'm not going to discuss multiple imputation during this talk. We're going to stick with interpolation. The D4I team was tasked by USAID to conduct an impact evaluation of health system strengthening activities currently being conducted in the DRC by the Integrated Health Project, or the IHP. This project aims to reduce maternal, newborn, and child deaths through the delivery of integrated health services. And the primary objectives of the IHP are to increase access to and use of the quality health services in the health zones that are targeted for action. As part of our evaluation, D4I posed the following research question. What was the impact of the IHP on the utilization of health services over the course of the study period? As an example, did clinic attendance for treatment of certain childhood illnesses increase or decrease relative to non-intervention sites as a result of the work that the IHP is doing? The analysis approach that we took, that we settled on, was a difference in differences with propensity score matching model. And of course, we're using DHIS2 data for this analysis. So there are other and related aspects to the impact evaluation that I won't discuss here, but note that the D4I project has also relied on primary data collection through quantitative and qualitative studies. So I just want to say a few things about propensity score matching, because this is where we applied, well, this is where we really needed to assess the missingness of the data that we pulled down from the DHIS2. So the approach we took was used to identify control health facilities using DHIS2 records. So we extracted a multi-month pre-intervention time series from the DHIS2 for facilities that would eventually be included in the treatment health zones, as well as those outside of the IHP targeted health zones. So we were able to make use of dozens of DHIS2 data elements to align control and treatment facilities with similar characteristics as far as clinic attendance rates across these data elements. So the overall pool of matched control facilities is serving as the comparator against those facilities that are actually receiving the IHP package of interventions while ensuring similar baseline characteristics. However, when the DHIS2 data element time series have missing data, complications arise in the propensity score estimation process, which is to say that the statistical validity of the PSM is threatened in the presence of missing data. So interpolation or imputation approaches can provide a solution for handling missing data in the steps we carry out to estimate propensity scores. And it's recommended to account for missingness before calculating these propensity scores. And this is, of course, where the notion of interpolation is coming into play, a notion that this webinar is clearly going to explore. So some of the issues with DHIS2 data, unfortunately, not all data elements in the DHIS2 are well reported, and it's typically necessary to clean DHIS2 data, which may include a process that accounts for missingness. In some instances, there are health facilities that have been added to the DHIS2 system, creating a scenario where missing data exists for all time points before the facility was added. Certain health facilities are also seemingly rendered defunct, for which an early time series exists, but for which subsequent time points are completely missing. Zero counts are typically not entered into the DRC specific DHIS2 system. There are zeros, but by and large, I think these are just not entered, making it impossible to distinguish between truly missing values and zeros. This is something that we're really going to focus on and look at in a couple of slides. From time to time, there are very large values, which are likely data entry errors. And additionally, reporting has generally improved over time, making earlier time points less complete across health facilities than later time points. So why do we care about missingness? I kind of alluded to this just a few slides ago, but missing data is a problem because nearly all standard statistical methods presume complete information for all the variables included in the analysis, and absent observations on some variables can dramatically shrink the sample size. As a result, the precision of confidence intervals is negatively affected, statistical power weakens, and the parameter estimates may be biased. So when it makes sense to do so, a researcher might try to fill in missing values in order to create a more complete data set. Well, we're going to start by exploring an actual data set that I pulled from the DRC DHIS2, which covers a 24-month time period and includes 1,362 facilities. And all of these facilities are from the Haut-Katanga province. I just focused on one province just to save on processing time as I was working through these data sets. I pulled this data set for combined counts of uncomplicated and severe malaria for all ages. And from an initial look, when I plotted the monthly aggregated time series for all the health facilities, it appeared to have a seasonal and positive trend component. And we'll talk about this in a little bit as well, why that might be important. So I'm just showing the slide to help people understand what they're about to see. And the figure here, the time series data are displayed in an Excel file where missing values are black. I just did this on my own. And the actual values are in gray. And the same principle is applied in the following slide. So this is an actual time series, multiple time series. So let's just be clear, each health facility is itself a time series, and all of these are just stacked into a data set. So this is for uncomplicated and severe malaria for all ages for the Haut-Katanga province. And you can see it goes from October 2018 to September 2020. I ordered these data so that the health facility records with the fewest missing values across their time series are on the top, and the ones with the most missing values are on the bottom. And you can see this nice gray area right here, no missing values, that only corresponds to 284 facilities out of the 1,300 plus. So you can imagine that if you were going to do a complete case analysis and just take these 284 facilities with no missing values, that you would literally be dropping hundreds and hundreds and hundreds of records from your data set, which may in the end bias whatever it is you're trying to analyze. For this particular pull of data, the overall missingness is 28.6%. So out of all the squares here, 28.6 are missing values. You can also see these really long stretches of missing data for a fair number of facilities. And there are a few that have never reported any data ever. And these are on the very, very bottom. So there's a handful of facilities that just, maybe they're just not, they just don't take patients. It might just be some other sort of facility, I don't know. But we'll take a look at one way to handle this scenario of missingness and the corresponding assumptions that we would need to make when we do that. And I just put down in the bottom corner here, I used R for all of this. And so whenever I show like an image or I guess, yeah, whenever I show a figure, I just wrote the name of the package on the bottom in case anybody's interested. So this is just a histogram of missingness. Just one more visualization. I basically just wanted to demonstrate that over 600 facilities, or about 45% of the data I pulled down, have 2 or fewer missing data points across their time series, and that's these 3 bars here. So this is the 284, all these perfect, nice gray ones here. But then there are 193 facilities with 1 missing value and 137 with 2 missing values. And then these 27 down here were completely blank records, and that's the 27 at the very bottom here. Just one more way to visualize. Yeah, and of course, if you were going to do a complete case analysis with the way these data stand as unprocessed, these are the ones that you would be taking. And generally, these tend to be larger facilities, hospitals and such. All right, so this figure shows the average values across all health facilities in the data set for each time point. So I literally just, for the first column here, I just took the average, second column just took the average, and then I just plotted it. So this might actually be a good way to show seemingly anomalous data points. Here we see 2 peaks. I'm pointing them out with the orange arrows. So the question we might ask ourselves when we see something like this is whether they represent legitimate peaks or outliers. And one way of thinking about this is if these peaks represent a malaria outbreak, for instance, we might see high values at these time points for multiple health facilities. If they represent egregious outliers, maybe only 1 or 2 health facility time series might have very high values at these time points. It's just one way maybe of conceptualizing this. Doesn't mean it's the absolute capital T truth. It's just one way of thinking about it. So we can use a package in R called anomalize to get a better sense of whether these peaks might be outliers. Here, the first peak in the red circle right there, I hope you can see my mouse. We'll do this. It's showing up outside of the range within which values are expected based on the information provided by existing data points. The second peak over here, while certainly higher than all of the other peaks, aside from the flagged outlier in red there, was itself not flagged as anomalous. And just to be clear, this figure, these data points are exactly the same data points here, except the anomalize package works through an algorithm to try to determine whether or not specific points are anomalous compared to the other points. So something looks off with this point here. So we can assume that it's an outlier, and we can try an approach to clear these outliers, however many there may be. But what approach should we take, or what approaches exist? Well, of course, if you do a quick Google search, you're going to find that there are multiple methods for handling outliers. And depending on how your time series behaves may dictate the level of sophistication necessary to identify and remove outliers or anomalous data points. One method is to remove values that are plus or minus X standard deviations from the median. It's sometimes advisable to use the median as opposed to the mean, because the mean is, of course, influenced by the extreme values, whereas the median is relatively insensitive or insensitive to these extreme values. You might consider experimenting with different thresholds, plus or minus 4, plus or minus 4.5 standard deviations from the median, plus or minus 8. I've seen as high as 8 used in certain publications. To examine what happens to your data when you apply this cleaning rule, which is to say, assess how many data points are actually removed upon application of this cleaning step. If you're doing plus or minus 2 standard deviations of the median and removing, I don't know, hundreds of data points, it's probably not the best approach, because in my opinion, what we're attempting to do here is really just remove those egregious outliers, those that are in all likelihood data entry errors. Somebody was entering data into a single cell, but maybe forgot to push enter or move to the next cell and just kept entering this new data points into the same cell though. So, and my apologies if this is too elementary, but I just wanted to show what it is that we're actually trying to do. And this is just a quick visual of the time series median, which is the black line. This is the median. So all these red lines are the malaria case counts. I calculated the median and just plotted it. I also calculated the standard deviation, which is the green shaded area. And then if we calculate 4.5 standard deviations from the median, the blue is how high that is. And you can see that we would only be removing in that case this one malaria case count, this 1 month worth of data, and something is clearly off with this value. Is it possible that it could be in an outbreak? Well, I don't know. Like sometimes it might help to actually look at the the population of the health area, if it exists, or the population of the health zone, to see if some of these values are actually beyond what the actual population is by a significant amount. In any event, this is the rule that I applied, plus or minus 4.5, actually just plus standard deviations to the median. Anything that was above that, I just deleted from the data set. And here we go. Okay. And just a quick digression. When I'm talking about removing outliers, I'm really only interested in removing those that are far, far beyond other data points in their time series. This figure shows 2 health facility level time series depicted by the anomalized package. If we focus on the top image, we see there's a huge outlier compared to other points in the time series. This would likely be a data point targeted for removal as in a quote unquote egregious outlier, and possibly represents a data entry error. There's something clearly off. It's thousands and thousands of cases higher than what you would normally see. And this is an actual health facility. This second one here, the second panel, shows an individual health facility time series with 4 anomalous points as detected by the anomalized package. But I'm not really interested in removing these values, as they may be legitimate data points. I'm really truly only interested in these crazy ones. So the top image here is the same image we already saw above. I applied the cleaning rule to all 1,300 plus individual health facility time series, where I calculated the health facility specific median and standard deviation, and then removed any value that was beyond 4.5 standard deviations from that particular time series median. In the Haut-Katanga province data set that I pulled down, there were just over 23,000 data points, actual reported values, and we're only treating 8 of these values as outliers by replacing them with blanks. So when I applied that rule of deleting any value beyond 4.5 standard deviations from the median, we removed 0.025% of the data. And you can see that these peaks were flattened. In all likelihood, they were data entry errors. I'm just going to make that assumption and move forward with the analysis. If we had removed 2 or 3 or 400, I would have revisited this. For me, yes, it's nice to have a standard rule that you can follow time and time again, as far as setting a threshold. But I think it's important to examine what actually happens when you apply this rule. So moving on, are missing values actually zeros in the DRC DHIS2? The short answer is that some, but clearly not all, missing values are likely zeros. This image shows the average number of missing values by health facility caseload. So facilities that have a smaller median number of malaria cases have a higher average number of missing values compared to larger caseload facilities. So this suggests that missing values may actually be zeros in the smaller facilities, which is what we'd expect to see. However, there are still a fair number of missing values, on average 3 to 4 for this particular 24-month time series, and the larger caseload facilities where we wouldn't necessarily expect to see missing values. Of course, these are just generalizations. So let me just reiterate for a moment here. So I took the median caseload for each individual health facility in the data set, and I binned them. So if it had between 1 and 15 for the median number of cases, all those facilities are here. And on average, there's about 10 missing values across the 24-month time series. Nearly half of the data are missing in smaller facilities. But as you get to the much larger facilities, 150 monthly median cases, we're looking at 2 to 3 missing values across that 24-month time series. So you can make that, well, let's make this assumption that the lower median case counts, the median case counts, the higher the number of average missing values, which kind of fits with that paradigm of whether or not these missings are zeros. For the most part, let's say that we can make an assumption that in all likelihood, they may be zeros for these smaller facilities. So do we just assume that all missing values are actually zeros, which would be akin to assuming that there's no item non-response, that is, no value is ever missing unless it's a zero? Well, the slide above suggests that this is probably not the best approach to assume this notion. We can assess an exaggerated example to see what happens when we replace one missing value from a large caseload facility and one missing value from a small caseload facility with zeros. So back to the anomalized package. So I took, these are 2 health facility time series that I took from my data set. And for both of these, I deleted 1 point and then just replaced it with a 0, just to see what would happen. So this is a large caseload facility. These are all malaria cases still. can see between like 1,000 and 2,000 cases, but all of a sudden there's a missing value at the third to last month. If we assume that it's 0, just a blanket assumption when we handle the cleaning process in our data sets, that 0 is going to show up as an anomalous data point. It's based on the time series, it's unexpected. However, in a small caseload facility, if we delete the value that was here and replace it with a 0, it's not necessarily unexpected as far as, well, the anomalized package is concerned. It's much less of an issue, I suppose, with respect to the unintended introduction of an anomalous point. So at this point, I asked myself, what's the best way to proceed as far as handling missingness? And through consultations with colleagues and reading, I wanted to explore the use of interpolation on the DHIS2 univariate time series that I pulled down. So let's take a look. So when we pull down the DHIS2 data that we're extracting, what we're extracting are health facility level univariate time series, which is simply a sequence of single observations at regular successive time points. In this case, it's monthly. These univariate time series may have an underlying structure composed of a trend, cyclical, seasonal, and irregular components. And when conducting interpolation on a univariate time series, it's possible to use these characteristics, the trend, the seasonal components, to aid in the interpolation process. And just so we're clear, interpolation estimates a value from other observations from the same individual or health facility, and it's usually applied to longitudinal data. So this is the seasonal decomposition of the average malaria cases for the entire Haut-Katanga province for a 45-month time series. So I expanded the time series for this example. Starts back in the beginning of 2017 and goes through, well, almost now in 2020. So the top panel is the actual plotted data. This is what it would look like if you just took the average for every single month of all the health facilities and plotted it. The second panel shows the seasonal component. So when you decompose, the package you're using or the command you're using is trying its best to find whether or not there's a seasonal component to find a trend. That's what the third panel here is. It's showing a trend. So you can see in the unprocessed or raw data that there seems to be an upward trend, and that's depicted here. So the package is able to identify that and plot it. This might also be considered a deseasonalized trend. Yeah, and just because the base stats package in R has depicted a seasonal component, that doesn't actually mean that there is seasonality to the time series. To better assess seasonality, we can look at an autocorrelation function plot, which is here. So this is an ACF plot. We notice a slow decay in the vertical lines here at the beginning of the ACF plot, which indicates a noticeable trend in the data. So if we go back and look here, we can see kind of a sharp rise, trend here, and that's definitely depicted here in the slow decay of these vertical points. If this time series had included a strong seasonal component, we'd see the lines flipping direction, up and down at somewhat regular intervals, and the lines would be extending beyond the blue dotted lines. We don't necessarily see that. There might be some seasonality in the beginning, maybe not so much as we move forward in the time series. And this is just a figure I took off of Google Images just to show the presence of strong seasonal component to a time series. So this is just the raw plotted data, and this is what sea level anomaly. So you can see that, yeah, there's kind of a clear seasonality here. And when you look at the ACF plot, you can see those vertical lines flipping back and forth, back and forth, back and forth with some regularity. And the vertical points are extending beyond the dotted lines. So you could make the assumption here that this time series has a strong seasonality to it. And that matters when you work through interpolation, if you choose to use an interpolation method that that takes into account the structural components of the time series itself. So we need to consider two basic assumptions of interpolation, which are that our time series don't have any violent or unexplained fluctuations in, for us, it's malaria case counts. Also that the rate of change, the increases and the decreases between points occurs at a uniform rate. So starting with linear interpolation, it's probably the easiest strategy as far as understanding what's happening to your data. The simple linear interpolation approach it's quite easy to code. It can be done with one line once the data are arranged in long form for this particular command. So this is called the NA interpolation function. And you can actually set how many gaps, how many missing gaps you want it to interpolate over. So if you don't want it to go beyond 2 missings in a row, you just put 2 here. If you want 6 or 7, whatever, you can write whatever you want. If you're interpolating across multiple univariate time series, you can accomplish this by using, for instance, the dplyr group by function on the health facility ID. Linear interpolation is probably a better approach to handling missing data in the larger caseload facilities as opposed to replacing with zeros. And using this approach on small caseload facilities, it may not grossly deviate from the truth. And that's what we saw a little ways up when we looked here. If we were to do, actually, I'll show you as we, oops, sorry. So let's explore that. So linear interpolation simply joins known values with a linear segment. It's probably easiest to conceptualize this with a graph, and many of you may already be familiar with this process. Just in the table here, let's just pretend that this was a time series and we're missing this value. You can plot that, and we have a value of 30, a value of 90. Just draw a linear segment between them, and we have 60. So that would be our interpolation approach. This value would be 60. Same thing here, just join these 24 and 124 with the linear segment, and you just pluck the values out and put them in your data set. So if you remember from the slide above, I initially replaced the missing values with 0, and these two time series. This was a large caseload facility and a small caseload facility, the results of which produced an anomalous value in the top panel here when we replaced this missing value with a 0. All right, if we replaced it using linear interpolation, it appears to be better suited particularly for the time series in the top panel. And down on the bottom, if we did linear interpolation here, instead of replacing with a 0, we'd get a value of 5 instead of 0. All right. So what if there's apparent seasonality to the time series? Here in the top panel, we see a time series with the periodicity of 12 months, January to December, just repeating itself over each year, and a handful of missing values. So I highlighted the missing value at August 2017, right? The second panel shows the results of linear interpolation, which in this instance is literally just the average of 64 and 104, which I show here. So the interpolated value is 84. The bottom panel takes seasonality into account during the interpolation process. So what actually happens is that the seasonal component is removed from the time series, and on the remaining component, a linear interpolation is conducted to impute the missing value, and then the seasonal component is folded back in. So not only does it take the side values into account for the linear interpolation component, but it's also looking across well, let's just say the seasonal component. So we get a value of 73 as opposed to 84. These are the same time series, just to be clear, just a different way of interpolating the values. So there are at least two approaches, I'm sure there are many more, we can take to account for seasonality in our time series. So one is the NA-interp function from the forecast package, and the other is the NA-struct-TS, so that's structural time series, from the zoo package, which actually uses a Kalman filter to interpolate missing values. There's some really good YouTube videos on the Kalman filters in case anybody's interested that really really make it clear what's happening. These two functions use similar mechanisms to interpolate missing data, and that they both can, quote unquote, handle seasonality in the time series. And just to visually depict a seasonally adjusted time series, because that's kind of what's happening when you use these packages. The red line, this is just another example I took off Google. The red line has obvious seasonality to it as you move across time. And this seasonality has been removed from the blue line, which is referred to as seasonally adjusted. And certain interpolation techniques will conduct linear interpolation based on the blue line, if there are any missing points, and then fold back in the seasonality to get a final interpolated value. So we've talked about visualizing the data to assess and address missingness patterns and any anomalous data points. We also talked about a few different methods of managing blank values in time series. So let's reset and apply these steps to our malaria data set to see what happens when we plot the overall monthly aggregated average values in our time series. So if we were to do a complete case analysis, as I mentioned before, we'd be stuck with the 284 health facilities here that have no missing data. Almost 1,000 other facilities would drop out of the analysis. But what are we going to do with these big sections of missing data? We could remove those facilities. Sorry, I'll say we will remove those facilities that have never reported anything ever, those 27 facilities. And assume that facilities with no reported data for X months in a row are either newly added facilities or defunct facilities. So this is where you need to apply a decision rule. If you don't have this information available, if you can't find a list of when facilities came online or when facilities were decommissioned, you may have to make an assumption or decision rule on your own. Maybe it might be if a facility has never reported for 12 months in a row, you might consider it either a new facility, depending on the directionality, a new facility or a defunct facility, or maybe it might be up to 18 months. It's worth exploring this and seeing how it affects the overall size of your data set. So if we remove those facilities, remove all these ones that I just used a rule of 12. If it had 12 or more missing values in a row, I just dropped it from the data set. And this is what happens. This is what's left. So we go from 28.6% missingness to 13.8% missingness. That's what we have left. And at this stage, we could just apply linear interpolation to these time series. And for instance, maybe you just wanted to do it for those time series with gaps less than or equal to 2 consecutive missing values. I've seen that in some published papers. I think people have an aversion to doing linear interpolation across multiple consecutive missings in a row. We could also apply an interpolation technique that takes the seasonality into account and assess the difference between all these interpolation techniques. Another approach would be just to replace all the missing values with zeros under the assumption that the only reason these values are missing in the first place is because a 0 was recorded on the initial health facility report and just wasn't entered into the DHIS2 system. So let's kind of look and see what happens if we do all of those. If we did linear interpolation and limited it to only those facilities that had gaps of less 2 or fewer, this is what we'd be left with. We'd have 807 facilities with no missing data just by applying this simple linear interpolation approach. And this accounts for 80% of the remaining data set minus those facilities that had long runs of missingness. Okay, so the complete case analysis on those 284 facilities is likely including those facilities with larger malaria caseloads, as there are no missing values included at all. This is probably why the monthly values are consistently higher than any other time series. So the blue line is the complete case analysis, the 284 facilities. The black line depicts the scenario where all blanks were filled in with zeros, which, as you can imagine, would pull the average down compared to the complete case analysis. You can see, though, that it retains the shape. The red line is the linearly interpolated data, where seasonality was not explicitly taken into account. And the green line depicts the scenario where we considered the structural components, the seasonality of each health facility level time series. So I guess the question we ask ourselves at this point is, which one is closest to the truth? We can try to answer this question by taking a full data set with no missing values so that we have a quote unquote absolute truth that we can graph. And then we can ourselves introduce missing values into this data, into this data set, and then apply our imputation techniques to see which method brings us closest back to the truth. So let's try that. So in order to run diagnostics on the performance of each imputation method, we'll start with the full data set because we need something that represents the truth. Here we go. Okay. So I pulled down a data set with just over 2,700 health facility level time series covering a 45-month period from January 2017 to September 2020. I pulled health facility records from anywhere in the country in DRC that had a value for all 45 months. I wanted to be sure that the original data set had zeros. So myself, I replaced 50% of all values less than or equal to 15 with a 0. And that gave me 0 values for 2.5% of all data points in the data set. Next, I randomly deleted 15% of values from across all the health facilities and time points. Then I deleted 90% of all the remaining 0 values to recreate the scenario where 0 values aren't recorded as such. Finally, I made sure to include missing data runs that were greater than 2 consecutive missing values in a row. And in the following slides, I'll show the application of various interpolation methods and diagnostics for the 2 interpolation strategies that consider seasonality. So this is what the data set looks like. There are 2,712 individual health facility level time series covering the 45-month period. You can see there's an overall missingness of 18.7% down here. You can also see some long stretches of missing values near the bottom of the figure. And obviously this is after I added in the missingness. To begin with, clearly there was no missingness because I made sure of that. And these are the results. So again, I took the average health facility caseload for here, January 2017. I took all the values that existed and took the average, and then did the same thing for February. And that's what I've plotted here, just to make it easier to show. All right, so the dark blue line is the quote unquote truth, which was plotted before I deleted any values at all. The lower black line shows the results of replacing all missing values with a 0. The upper red line shows the effect of conducting just linear interpolation on time series gaps that were less than or equal to 2 consecutive missing values. Of course, you can change this if you'd like. I just stuck with this threshold. The green and fuchsia lines are the graphical depictions of applying interpolation techniques that take seasonality into account. You can see that they're both nearly superimposed on each other, as well as the line that's representing the truth. Just eyeballing this would suggest that either the NA struct TS or the NA interp functions would suffice, but we can calculate raw bias and percent bias or difference to see which actually performed better. First, let's look at just one single health facility time series to examine how each interpolation function that takes seasonality into account estimated the missing values. So this is the NA struct TS structural time series packet function in R, and the red points are the ones that were interpolated. And this is the same health facility on the bottom, but just using a different function, the NA interp function. And the red points clearly, are the missing values, the same time points. These ones look pretty similar. This one looks pretty similar, the interpolated points, but here you can see there's a difference. The NA interp function put this missing value as a peak, whereas this one was not put as a peak. And these ones look pretty similar as well. So you can see that there's some differences between these 2 functions. They're both supposed to take seasonality into account, but one uses a Kalman filter and one doesn't. So I took the raw bias, or you can just say the difference between the interpolated values and the true values, just simply a subtraction. And then I averaged those across each of these functions. And you can see that the average raw bias is, it's basically the same. There's really not that much difference. The structural time series function is slightly more compact around the zero line bias, which is, I guess better, but really, I mean, as you saw in the graph above, basically these lines were superimposed on each other. So this was just the raw difference between the values. This one was the absolute value of the percent difference. And again, this is called the mean absolute percent error. And if you're reading around and looking at ways to diagnose or conduct diagnostics on your interpolation methods, this is one that'll pop up quite often, the mean absolute percent error. Basically the same. Again, the blue one, which is the structural time series function, was slightly more compact. You can also look at the root mean squared error. So in the simplest of terms, and in the context of our example here, the root mean squared error, or the RMSE, is a measure of how well the interpolation performed. It measures this by calculating the difference between the interpolated values and the actual values. It's pretty easy to find a formula for this. Here we see that the RMSE for the NA-struct-TS procedure was lower than the corresponding RMSE for the NA-interp procedure for nearly 70% of the individual health facility level time series included in our data set. This suggests that for the most part, the NA-struct-TS function performed, a little bit better. But note that the root mean squared error it may not be a good diagnostic tool if there's a strong trend to the overall time series. So just a recap. These are the steps that I work through. That's not to say that they're static. My understanding of DHIS2 and managing the data in these systems is evolving. The more I read, the more papers that I work through, subject to change, let's just say that. So the first thing I do is assess missingness. Can I do a complete case analysis? Would that seriously affect the results that I'm trying to show? I address egregious outliers and, find a suitable threshold beyond which data are deleted. Manage the new and defunct facility records. So ask yourself, or ask people who work on the system, what constitutes a new or defunct facility? How can you identify them? How many consecutive missing data points are you willing to accept as you work through a process to handle missing data? Decompose the time series. Do your time series appear to have a strong seasonality to it? You can examine that with an autocorrelation function plot. Try a few different interpolation techniques and plot the results. Which interpolation technique makes the most sense, giving the missingness attributes and the inherent structure of your time series. Try to isolate a subset of records with no missing data, and maybe yourself work through this, introduce missing data and recreate the truth, just to give yourselves a sense of how these data behave. These two papers here I thought were fantastic. The one by Stefan Moritz was really useful. He worked through, I think he's actually the architect of one of these R packages called Impute TS. And there's a paper that he wrote with his colleagues that looked at the different types of interpolation functions within that package to see how they actually perform. This other paper here, Interpolation and Time Series, was also a nice paper to read through. And, sometimes these are difficult to understand. Sometimes they're full of mathematical formula, but reading through particularly the introductions, and you can kind of like pull out some decent pieces of information that help frame how you might move forward as you handle missing data. That's it. That's all I wanted to share. I hope you all have some good questions.
Great, thank you, Matt. So there are a number of questions in the Q&A, Matt, if you want to go through those and just sequentially answer those.
Okay, so, and Jessica, let me know if I'm not on the right page, but so this is the first question. The calculated standard deviation is for the median, represented in blue color at the graph. I'm not quite sure what that one's referring to. This one? I think that's what it means. Yes. The standard deviation. So I did 4.5 standard deviations from the median, and that reaches a height at the top of this blue shaded area, which is about 3,700 or so. When you remove the value, is that just for one health facility, or are you deleting the entire month? Well, these data are reported monthly, so we only have monthly values. So if a particular health facility time series has, for instance, this one here, this one would just be deleted, whatever this value was, 4,200 or something. Just working under the assumption that it's a data entry error, yes, I would remove it, and then I would interpolate over it. Okay, here's one. Is there any guidance or thoughts on what plus or minus standard deviation threshold to use to flag outliers? During 2020 in countries where we anticipate disruptions due to COVID, particularly for analyses with the goal of estimating disruptions due to COVID. And as such, we don't want to remove real values reflecting real disruptions. Matt, how would you assess which threshold is appropriate in this context? Yikes, that's a good question. So I'm assuming that this has to do with lack of visits to health facilities, like underutilization of health services because of COVID. Maybe it's because people are staying away from facilities. So I'm not sure that you're going to be dealing with egregious, like huge values. Maybe it's the opposite notion of what's presented in this question. And please type your question or give clarification if I'm off base here. In which case, maybe it makes sense. Well, now I'm guessing whether or not these values would just be much, much smaller. Yeah, I think the notion of plus or minus whatever X standard deviations from the median is really to address outliers and not to address real trends in health service utilization. Yeah, please feel free. Maybe I'm not quite understanding that question, but feel free to type something else. I'll just move on to the next one. Instead of removing the extreme outlier, why not revalue it at a value equal to plus or minus 4.5 standard deviations? Meaning to pin it, I suppose, at that top value. I'm thinking that's what the question is. I think looking at this picture here, if we were to just reduce the value of that large red bar to just the top of the 4.5 standard deviations of the median, I still think it's probably going to be an issue. I still think it's going to pull your trend in a particular way that may not be truthful or even meaningful. I think it might make more sense, in my initial understanding, would be to remove it and interpolate over it. Be nice to hear if anybody else has any ideas. If you are introducing missingness at random to a full data set as a sensitivity analysis, the assumption is also that in the DRC data set, missingness was also at random given facility size. It seems likely that missingness is potentially biased by something unobserved and not just facility size. Is there anything you can do to manage biased missingness due to unobserved variables? So I didn't just introduce missingness at random. I I isolated facilities that were small, and I replaced those values with zeros. And then I targeted those same values with missingness. Of course, I did apply some random missingness across the data set, but I did focus on the small facilities. I think it's hard to assume that data are missing at random with DHIS2 data, particularly given this notion that in early time points, data might be more likely to be missing because of just a higher propensity of incomplete reporting versus later time points. I think that's also one reason that I have some hesitations with multiple imputation because some of the assumptions for multiple imputation are missing completely at random or missing at random. And if you have missing not at random data, you have to really understand why your data are missing and model that into the techniques you're using with multiple imputation. Is there anything you can do to manage biased missingness due to unobserved variables? I don't know. I think that's a good question. I'm not sure. All right, we'll put a pin in that. Did you look at missingness in a multivariate context? It is often useful to look at other data elements being collected in the same DHIS data set to differentiate between non-reporting and zero. Yeah, I've explored this quite a bit. So one method that we took was to take overall clinic visits, which is a very, very well reported data element in the DRC DHIS2, and just assume that if there is a value for overall clinic visits that for a particular month, that a missing value for another data element for that same month might just be a zero instead of a blank, because clearly a report was submitted. And so just make the assumption then that if a value wasn't put in, it was because it was a zero. I think that this is somewhat fraught because, as we saw, there are other health facilities, particularly those that are on the medium or larger size, that still have missing values and where you wouldn't necessarily expect a zero based on the overall trend. I think it's also difficult if you were to use an imputation approach using multiple variables that might predict missingness, because in the DHIS2, a lot of the data elements also have missing values. You can't, predict missingness with a missing value. But yeah, I think that's one approach that might, you might also consider looking at the most well-reported suite of data elements and look across the same time points to see if they have values or not. And then if you're working with another data element, fill it in with a zero if it's a blank or something like that. But I think maybe what this question is getting at in the end is multiple imputation. And I think that there's some issues there with DHIS2 data that I still need to explore myself. Any ideas for a future state where a DHIS2 app could auto-generate these calculations or something close to automated? I see that in the DHIS2 blogs or the forums. I started to pop up in my Google searches about doing auto-interpolation when people pull these data down. I think people are working on that. At least it's making its way into the conversation in some of the forums that I see. I don't necessarily think it's a terrible idea. Yeah, but I think, that's an interesting question, and I'm sure there's people smarter than me that are working on it. Can we have some examples to deal with missing values by having any household survey data? Can we have some examples to deal with, maybe you mean to deal with missing data in the DHIS2 by having household survey data? I'm not sure if that's what that question is getting at. I I think, I'm not sure. I think health service utilization, which is what we're looking at with DHIS2, like overall case counts. And then going into the population and doing a survey on maybe some specific disease for which there's a data element in DHIS2 to see, you know, I mean, DHIS2 is about, it's about people that are using these services, right? At the root of it, estimating a missing value based on a population-based survey, household survey. I'm not sure that that makes perfectly intuitive sense right now. It's something to think about. On your time series, can you walk through the list of interpolation techniques by color on your time series? I'm just going to go to the last one, this one here. Yeah, just to recap, the blue one is the truth. That was before I introduced any missingness. I just took the totally complete data set and plotted it. The black line is where I replaced all the missing values with zeros. And just like we saw above, you can imagine how that would drag the average down. The red line is linear interpolation, and that was only with gaps of 2 or fewer missing in a row. And then the green and the fuchsia were in interpolation that took seasonality into account. If autocorrelation functions showed no seasonality, what is the reason to take seasonality into account when you apply the interpolation? I mean, I don't necessarily think it showed no seasonality. I think that it showed just not strong seasonality. And I didn't mention this, but the NA-interp function, by default, it will conduct linear interpolation, but if it detects in its decomposition of the time series any sort of seasonality, it will take that into account. So that the NA-interp function there, I think that's a really nice feature if you choose to use it.
Matt, I see we're at 10:04 here.
Okay.
I want to respect your time. I mean, we're able to stay on for a little bit longer. I think there's just a few more questions, but if we need to wrap up, we can do that as well.
Okay. I do have another meeting.
Okay. Okay, great. Well, we can, let's see, are there any others on? I think some of these were already answered. Or they relate to other questions. Well, thank you very much. We're sorry we didn't get to all of the questions. We appreciate your participation. And as we've noted in the chat and then also in the introduction, we will be sending the slides or a link to the slides as well as the recording of the webinar. So please look in your email for that. We will also have these materials available on the dataforimpactproject.org website. So you can also get them there. And please keep a lookout for our upcoming webinars. There'll be one of these basically every other month. So again, check in your emails. If you're already signed up for the Data for Impact emails, then you'll get that automatically. If not, you can go to our website and sign up for that. And again, just look on the website for anything that you don't get an email. Thanks so much, everyone, for joining us. Have a good rest of your day or evening. And we will talk to you again soon. Thanks.